Number 8. How many molecules are contained in each of the following? This is actually a little bit more of a review here. Now we're going to be using Avogadro's number here, and that states that in any 1 mole of any substance, there's going to be 6.022 times 10 to the 23rd molecules. Now the actual law uses the term particles, which is a little bit more comprehensive and describes more situations. But we are going to be talking about gas molecules right now, so let's just go ahead and say molecules. How many molecules are contained in each of the following? So I'm being asked for a number of molecules, and so I need this unit in all of my calculations. Now for A, B, and C, I'm going to be starting in moles, and so I'll simply do one conversion. But when I get to D, I'm starting in mass. So I'm actually going to have to go from the mass of this species into the number of moles of this species. Then I can use Avogadro's number to do my conversion. So here we go. You know what? I'm just going to go ahead and use this bad boy in my crosshairs. And the 1 mole is equal to 6.022 times 10 to the 23rd molecules. Moles cancel, moles cancel. This ends up being 6.022 times 10 to the 23rd molecules. Alright. B, same setup, converting out of moles and going into number of particles. Moles will cancel. And so now I can use a calculator. Now I'm not going to do anything to the times 10 to the 23. I don't like to mess with exponents in the calculator whenever I can avoid it. So I'm only going to do the coefficients there. That's a 2.50 multiplied by 6.022. And the value that my calculator tells me has too many sig figs, right? A little bit of calculator vomit. Looking at the value that the question gives me, 3 sig figs, right? This is 4, so that's not going to limit me. So I'm going to go with 3. Looking at what the calculator gives me, that's this value right here. This 5 tells me to round that up. So I'm going to go with 15.1. 15.1. Now, what do I do with this times 10 to the 23rd? Well, it's 15.1 times 10 to the 23rd. But that's not in scientific notation. Okay? This value is a completely legitimate value. It's simply not in proper scientific notation. Okay? It's absolutely a legitimate value. It's just not in scientific notation. In order to get it into scientific notation, I'm going to move the decimal 1 spot to the left. Now, I'm not going to regale you with the rules of if you're moving the decimal to the right or to the left, does the exponent go up or down? I'm not going to do that because, well, I mess it up all the time. But what I do know is that this value right here, the 15.1, the reason I had to move the decimal in the first place is because this value was too large to be in proper scientific notation. You guys remember that the coefficient on scientific notation has to be between the values of 1 and 10. This was above 10. It was too large. So when I move the decimal, I have to change the exponent in such a way to reflect the fact that this number got bigger. It got too big. So when I go to represent my final answer, I move the exponent up by 1. Don't forget to include your units. Alright, now we have a pretty small value here. Same conversion factor though. 1 mole. Avogadro's number of molecules. Mole goes away. We got ammonia right there. All that's left to do, plug in our values. I got some weird stuff going on here. Yep, that's right. And again, I'm not going to mess with the times 10 to the 23rd right now. I just want the value right. All right, so hopefully you guys can see that this is not going to be in proper scientific notation. So I'm going to have to end up moving that decimal one place to the right, because this number is too small to be in proper scientific notation. So that means I'm going to move the decimal one place. And because this number is too small, the way I change my exponent at the end needs to reflect the fact that it got too small. So that means I'm going to move the exponent down by 1. So it's going to end up being a times 10 to the 22. But we also need to consider the appropriate number of sig figs. Looking at the question, we're given 3. That's pretty common. So that's that value right there. That 4 tells me to leave this alone. So as I move the decimal so that that value is between 1 and 10, I have 3.91 times 10 to the 22nd molecules. And finally, D. Now we are going to have to do a two-part conversion here, but that's easy. We just slap on one extra conversion here. Now I'm going to have grams of NO2 right there, and then moles of NO2 up top. Why is that? Because in order to use Avogadro's number, my unit has to be in moles. So I have to convert out of grams into moles. In order to do that, I'm going to use the molar mass of NO2. So referring to my handy dandy periodic table, I see that there are 2 oxygens, each with a molar mass of 16.0 or 15.999. And we're going to add that to the mass of 1 nitrogen atom, which is 14.01. And so our molar mass of NO2 is 46.01. 46.01. Now, I did addition here at the end. So I'm actually going to keep that 0.01. I'm actually going to keep that 0.01. For every 1 mole. Now I can use that same conversion factor I've been using to get into molecules, which is what my answer is supposed to be in. So now you see grams cancel with grams, moles cancel with moles, and the only unit I have left is molecules. So, calculator, don't fail me now. See if I can get on here with not be in the way. 11.5 times 6.022. Again, not using the times 10 to the 23rd in the calculator because, for me personally, that messes me up. If you're better with the calculator than I am, more power to you. Okay, or if you have a nice graphing calculator that allows you to do that simply, more power to you. But that's just not where I'm at. Okay, so I have a value. Proper scientific notation? Yeah, that will be 1.5. That's between 1 and 10, so that's looking good. Number of sig figs? 3, 4, 4. I'm going to go with 3. Okay, so that 5 right there is going to tell me to round that up to a 1, so I'm going to end up with 1.51. I haven't done anything with that times 10 to the 23rd, and it looks like I don't need to do anything with that times 10 to the 23rd because that is going to allow it to be in proper scientific notation as is. I don't have to move the decimal at all. So my final answer is 1.51 times 10 to the 23rd molecules.